Today we're going to look at an exam question on total internal reflection and refraction from within the 2023 AS Unit 2 exam paper. So it starts us off by asking us if we can define the refractive index of a material. So the refractive index of a material, remember, is something to do with the ratio of the speeds. It's to do with the ratio of speeds between the speed of light in that material and in the vacuum. And if you have a look, your data sheet will help you out a little bit with this, but you do need to know the following definition. So I would always say that that N is the refractive index, it's a symbol we use for it, is equal to the speed of light in a vacuum divided by the speed of light in the material, so if that's glass or air or whatever it may be. Okay, so that's the fastest way of scoring those particular marks. That's the definition for refractive index. Now we've got a diagram here. There's lots going on the diagram, and we're probably going to need some of it early on and then more of it later on. It says, show that the refractive index of material A is approximately 1.5. So we'll start out by using from the data sheet N1 sine theta 1. Okay, so remembering that this is the first one, so this is the one going in, so that's going to be 65, this angle here, is equal to N2, so that's the second refractive index. That's for material A, I suppose, in this case, but that's going to be the second one it's going into, and then the angle it's coming out into that material at, so that's theta 2 as well. Okay, so there's a nice symmetry to this. And then if we just start putting in the numbers that we have, so N1 we've got from the question up here, which is 1.61 sine, and that's coming from here, 65, is equal to N2 sine, and we do know the angle here, which is 80 degrees, sine 80. A little bit of rearrangement, so this is a times over here, so it becomes a divide over here, so we can move that across, so that's going to be sine 80, cross it out from this side. So you see how I've got my equation here equals N2, N2 equals, so chuck all that through your calculator. I'll just demonstrate that for you now if you like, so you can see how it goes in. So it's just a case of laying it all in, 1.61 sine. The calculator always opens the brackets, so remember to close them. This is a divide, of course, so that's divided by sine 80, close that bracket again. Okay, that should have all worked out, 1.48, and that is our answer, 1.48. Okay, lovely. Determine the time it takes for the ray of light to travel through material A. Okay, so this is going to be a little bit tricky. We've got some steps to go through. So the first thing you need to recognize is that this is a triangle, and you can use your trigonometrical rules from Unit 1 in order to solve this. So the first thing we're going to do is we're going to acknowledge that we've got a triangle shape here, that we've got that angle there, and that this, I'm going to call the distance D, the hypotenuse of my triangle, is going to be, if we think about it, this is my adjacent, is 10 from here, from the diagram. So this is my adjacent, that's my hypotenuse, so I'm going to use the cosine on this one. So I'm going to say that D is equal to 10 over cos, and it's 80 degrees, so cos 80. That's going to equal, if I chuck it in the calculator, 58 millimeters. Okay, it's important to keep the millimeters there. You can turn it straight into meters now, but we'll leave it millimeters for a second. Okay, the next thing we need to do is from the data sheet, we need to steal N equals the speed of light in a vacuum divided by the speed of light in that material. Because I know what the refractive index is, and we worked it out here. I know what the speed of light is in a vacuum. That will tell me what the speed of light is in this material, okay? So we'll then just do a quick bit of rearranging. So V, the speed of light in the material, so we can call it VA if you like to avoid confusion, because that's V in A, is equal, so they're just going to swap over. So that's going to be C over N. So then if I do that, 3 times 10 to the 8, which is the speed of light in a vacuum. If you don't remember that, it's on the data booklet for you, over 1.48. And that's going to give me an answer of 2.03 times 10 to the 8 meters per second. There you go, that's important. You see how we've got meters here and millimeters here? Watch out for that as we go through. So now we're going to do some nice simple, back to year 9 physics. We're going to say that speed is equal to distance over time. I know what the distance is. I know what the speed is. I don't know what time is. So therefore, time is equal to distance over speed. So let's think about what that distance is. It came from here, 58 millimeters. Put that in right, or you'll mess up. Times 10 to the minus 3 for millimeters. All over speed, which we've just found from there. And that's going to all come out of my calculator as 2.86 times 10 to the minus 10 seconds. Underline it so we're really clear that's our answer. Okay. Got a little bit more to do on the next bit here. Confirm that the total internal reflection will occur at y. So if again we're leaning quite heavily on the data booklet for this particular question. So let's just remember, shall we, that n1 sine theta c. So theta c is this idea of critical angle. Total internal reflection occurs at the critical angle, is equal to n2 is equal to n2. Sorry, for a moment there I managed to have a complete mind blank. So n1 sine theta c is equal to n2. And that's because the angle sine theta 2 would be equal to, theta 2 would be equal to 90 degrees, and sine of 90 degrees is 1, so we can leave it out. We can just skip that from there. If we then plug our numbers into this, we can then go from there. So I'm going to bring n1 over because I'm trying to find sine theta c. So sine theta c is equal to 1.31 over 1.48, and that's equal to, so I'll bring the calculator back in so I can show you. So what I'm going to do is I'm actually going to put this bit in here first. 1.31 divided by 1.48, okay, and that's going to give me an answer there. Now, because I'm trying to find what the angle is, not the sine of the angle is 0.89, but here I want the actual angle, so I'm going to press the shift sine function, put in my answer just by using the buttons on the calculator, and then press equals, and that's going to give me 62.3 degrees. So 62.3 degrees. So that's what I've found the critical angle to be, and what we're saying is that that angle is going to be greater than so it's going in at 80 degrees. So 80 degrees, which is actually what the angle is greater than 62.3, the critical angle. Therefore, we'll get total internal reflection. Okay? And then they want us to finish off with a nice little bit of drawing over here. So they want us to realize, of course, that if we have total internal reflection, sorry, that's my notes. Let's try it on the actual one that they're doing here. Here we go. So if we take a look at this, how long is that? That's 4 centimeters, 5 centimeters, isn't it? So if we pop that on there, we're going for about 5 centimeters, which is going to be about there. So then when I draw my line, can't pick my ruler up, just putting it on here, and the exam board want you to draw this by eye, okay? So there's no great stress if those angles are slightly different, as long as they are close enough that you can pretend that they are reflecting, okay? I hope that helps. It's quite a complicated question. It's getting towards the end of that Unit 2 paper. The only way to get these, or to get better at these though, is to practice them. So I hope that's been useful for you. Don't forget, there's loads of other videos that you can check out while you're on the channel.